Welcome to a new episode of the Video Vision channel. Today we will talk about the ITER fusion experiment and about delays which have recently been announced. If you're interested in a German version, you will find it on the Urknall, Weltall und das Leben channel and you will find the link below. So today I will speak about ITER. Maybe not surprising, we already had a video about ITER and about technical problems with the chief scientist of ITER, like I think half a year ago, and you will find the link for this below. So on the 3rd of July 2024 there was a press conference by the ITER Director General Pietro Barabaschi, who announced a new timeline and a new budget for ITER. And if you looked in the news, in fact, you could recognize very quickly how this was taken up. So I have here something which says, ITER fusion reactor hit by massive decade-long delay and 5 billion price hike. Then if you look at the press release which goes with this, where I have put in the corner right down the link in the web where you can find it, it says full magnetic energy in 2036, which is 3 years delay. Deuterium-Tritium operation phase 2039, which is a 4 years delay, which is not really the same as 10 years or even, I think it said, decade long. And so what I want to talk about in this video today is how do these things fit together, what has really happened, and why can you come to such different numbers. And so I said already, ITER is hit with a delay. We talked about this. There are problems in the components, how you put together the large components, the vacuum vessel. You might want to look at the video, which we just linked down there. And it was clear after some time that you could not hold the initial date for ITER operation, which was supposed to be 2025. So starting next year. I think it's always 31st of December of 2025 in any year in these time plans, but this was the idea. So what was then done was actually a rigorous assessment of the problems. Also a repair method, which we talked about already, is now underway and being executed for the things which were not fitting. But there was also then the idea to come, or the urge to come up with a new time plan, which was then done on this 3rd of July press conference. And if you look at this in detail, you will find that ITER has not only shifted everything by a certain delay, but has completely changed its approach, how they would take into operation the machine. I personally find this a very clever strategy, because if you have a delay, you might think, okay, can I deal with this delay and do something else? Because now I have more time, can I do something else than before? And this is exactly what they did. And so if you sum it up, in my opinion, this is a delay of 3 to 4 years and not 10 years. But of course, it looked different in the newspaper. And to explain this in more detail, I have done the following thing. I have looked at something which is called the ITER research plan, which you also find on the internet. And this is dated in this version I have here, September 17, 2018. So this was done 6 years ago, almost. And it is the thing which was the reference for how ITER would be taken into operation. Now, if you look at this ITER research plan, it is a very long document created by the scientists participating in ITER, and they spell out how they want to take into operation the ITER machine. And so if you look on one of the pages, sort of in the beginning, you will find an overview which looks like this. So there is indeed the first plasma in December 2025. So this is the date we were talking about, which could no longer be held. However, you notice if you look what this means in the description, it means 100 kiloamps plasma current. If you have seen some of our videos, we talk in present-day devices about 1 to 5 megamps and ITER 15 megamps. So this is really only a plasma to show the device is working in principle. The idea was always you do the first plasma, you do just a sort of, we call this pink glow because there's a glow of plasma in there, and then it's over. And you can see this was going to be followed by an assembly phase, where then only in 2028 you would start with something called pre-fusion power operation, which was proposed to be done at half field and half current. So still not the full performance. And in hydrogen and helium, which do not create any nuclear reaction here. There was another assembly phase, which you can see here, following after that. And then there is pre-fusion power operation 2, which was going until March 34. This would go and take the machine to the full magnetic energy in 2033, in between this phase from 32 to 34. And this is exactly what I showed on the slide before. This is now moved to 36. So to summarize this, and then there was another assembly phase here after this, and then DT, deuterium tritium operation, would start in 2035, and this is what has now been shifted to 2039. So the upshot of this is that the ITER team has looked at, can we change our strategy to commission the machine and to take it into operation so that it is not 10 years delay? And the answer is yes, we can do this, because we will now assemble the whole machine in one go, rather than saying we have these, in the beginning, not so meaningful experimental phases, and then we have 3 years of interruption or 2 years where we assemble stuff, and then we go for another operation, and we go. And so this change of the strategy has led to a new strategy, which in the end says that the most important things, for me as a physicist, A, you have the full magnetic energy, which means the full capability of the machine. This has shifted by 3 years. And then you start deuterium tritium, which is the thing to show that you create more fusion power than you deposit heat in the plasma or power in the plasma to heat it. This has been shifted from 35 to 39, which is this 4 year shift. So I actually think that they have done a pretty good job in trying to minimize the delay and change the commissioning strategy, how you would do this. And there is a very interesting aspect now for us here in Garching at the Max Planck Institute for Plasma Physics, because we also had a video about this. Since 1996, we have a program on ASTEX Upgrade where we study the use of tungsten as a first wall material for plasma devices. This is because tungsten has a very high melting point, and so you can use it in order to protect the walls, and it would not melt if there is energy coming on it. And then on the other hand, there is also a very low level of erosion of tungsten material, so there is a very low influx of impurities into the plasma. So this is something that we have done on ASTEX Upgrade, and I have here a slide. This is now in German. Excuse, there is a mix of German and English. And what it says, you see down here ASTEX Upgrade with its full tungsten wall. This worked very well, actually. So the JET, Joint European Torus Experiment, decided to also put in a tungsten wall. ITER was at that time building on 3 different wall materials, beryllium, then in the main chamber, tungsten, and then carbon, for different reasons. After the successful experiments in ASTEX Upgrade and then JET, they converted to a full tungsten diverter and still had this beryllium on the wall, which was there because it's a material with very low atomic number. So if it comes into the plasma, it would only put a very small amount of radiation. On the other hand, since we had now shown you could go with full tungsten, and a reactor machine, a fusion power plant, would have to go with tungsten as well, ITER made a smart move and said, now that we have more time, let's go to a full tungsten wall. So you could argue that now ITER has the wall that we have on ASTEX Upgrade, and it will actually go into operation with this. So while it is shifted, I would also say one of the benefits of this process, although we're not happy about the 3 respective 4 years, one of the benefits is that it will start up with a inner wall, a wall material which is fully reactor compatible and will be much easier to extrapolate to what will be done in a fusion power reactor. So if we go back to the initial thing, is it 10 years? I don't think so. 3 years for the full magnetic energy. It is 4 years for deuterium tritium operation. Are we happy about it? No, of course not, because it is a shift of 3 respective 4 years. But I think looking at how they changed the strategy and adapted to this in actually communication with the Worldwide Fusion Program, they have made the best job that you could do with respect to this delay. So I think this puts a bit into perspective these headlines in the newspaper. As always, if you have questions, comment, you can leave them down here. We will look at it. I will be happy to comment on these.